Okay, so today we're going to talk about some probability basics. I'm going to start with a very, very simple question that hopefully almost all of you should be able to get, especially those of you who have had my intro class, but that might not be so easy to answer after all. So, I have a coin. Turkish lira has a heads and a tails. What's the probability that a fair coin is going to turn up heads? 0.5. 0.5, that's exactly right. 0.5, if you want to express it as a percent, you would say 50% of the time. There's a 50-50 chance it'll be heads or tails, right? 0.5. So, 0.5, duh, right? All of you guys hopefully should have gotten this. How did you know this? This is the interesting part.
Because there are two options and it cannot come out heads and tails at the same time.
There are two options. I can flip it and it can turn up heads or it can turn up tails. And it can't turn up both at the same time. Right? Turkish liras are a little different than some American money because they're a little bit fatter. So it's possible that it could land on its edge like that. But let's just say if that happens, we'll flip it again until we get something like this. So there are two possible outcomes, right? Heads, tails. It's going to be one of them, right? So you can say there are two ways a fair coin can turn up. Heads or tails. Each of these things are known as an outcome. One outcome is heads, one outcome is tails. Together, these two outcomes form the outcome space. The outcome space is basically a collection of all of the outcomes that we could potentially observe. Does that make sense? So with a coin, we can observe a heads or tails. We could potentially throw in on its edge in the outcome space too, but like I said, if that happens, we'll just flip it again. So we're not going to worry about that in our outcome space. We can talk about other outcome spaces too. So let's talk about biological sex.
What a day.
You know, this is what happens at the beginning of a school year. You have these pens that used to work so well, but then over the summer your daughter came in and wrote with them. All right, so I'll keep trying this throughout the day. Maybe we'll get something. Maybe not, but let's think about biological sex. What is the outcome space? If I was interested in finding out what the probability, I was picking a random student in this classroom, what the probability is that they're a male. What is the outcome space?
Male or female?
I guess male or female.
Yeah, male or female. It's this binary thing, right? It might get a little bit more complicated. If you're taking biological psychology, you may learn that there's more than just XX and XY. There are things like XXY and XXXX. Lots of variations. But if we ignore those for a moment, we can say male or female. We can talk about the sample space of majors in this class. So we have a lot of psychology majors. We have some sociology majors. Last class we had a history major. Do we have other majors in here now? Looks like we have more people in the class now. That makes me happy. Any other majors? Cinema and television? Philosophy? Law? Religion? No, that's it. So what is our sample space? If we're talking about majors in this class?
Currently only two, yeah.
Not two.
Three.
We've got the three. We've got the psychology, sociology, and also history. Is the history major here today? So today the sample space is only the two. Okay, so, excuse me, I've got up on the board the outcome space. In statistics, sometimes you will find a number of ways of referring to the same thing. So when I said the sample space, what I was referring to here is the outcome space. On the study guide, the link that I point you to is actually a link to sample space, but basically they're the same things. They're the potential outcomes that you could observe when you are sampling from some population. Yeah. All right, so if we flip the coin, by flipping the coin, we will observe one outcome. Outcomes are sometimes known as simple events too, so I put this up here so you're aware of that. So flipping the coin is going to result in one simple event. This is known as a statistical experiment. We're doing some well-defined procedure that is going to produce an outcome. So, flip the coin. It's heads. That was a statistical experiment that resulted in one outcome. Are you male or female?
Female.
Female. This is a statistical experiment. It's a defined procedure that results in one of the two outcomes that we've defined. Are you psychology, sociology, or history major? Psychology. Sociology. She's a sociology major. That was a statistical experiment. Okay? So, let's make some formal definitions here. So, a statistical experiment, who wants to take a crack at it? Yeah.
It's when you're checking out the likelihood of occurrence of something, when the outcome is in doubt, and we
Okay.
have at least two possibilities.
All right, so see, she said a whole bunch of things. It's checking out the likelihood of something, and I'm actually going to strike this part off of the definition, because when people talk about probability and likelihood, likelihood is something a little bit different. And in a simple statistical experiment, let's say in the long run I might want to know what the probability of this turning up heads is. However, in one statistical experiment, I just get an outcome. I don't get something that says, aha, the probability is 0.5. Does that make sense?
Yeah.
What was the other part of the definition?
Outcome is in doubt.
Okay, there's some outcome in doubt. It's unknown. We don't know what the value is. That's actually good. I wouldn't have included that in my definition. That makes a lot of sense. We don't know what the result of the coin flip will be. Will it be heads? Will it be tails? I don't know. Woo, it's tails. So there's some outcome in doubt. Now, it might seem sort of silly for me to say, like, are you male or female? Like, because I can assess that fairly easily. But let's say that I didn't have the ability to assess things like that. I wanted to grab a random student from my class. I'm just going to pick a seat at random. So I put numbers on all the seats, let's say. And seat number 12, who's in that seat? You are. I didn't know, right? The outcome was in doubt. Female. All right, so there's some procedure that is done when there is some chance, when there is some doubt about what outcome might occur that produces a particular outcome. One outcome, right? Not a whole bunch of outcomes. I flip the coin, it's not heads and tails, or 3 heads, it's just one outcome. So statistical experiment, my definition was a well-defined procedure that results in the occurrence of some outcome, we can tack on her part, whose identity is unknown, is uncertain, right? How about an outcome? What's an outcome? So we said tails is an outcome, heads is an outcome, male is an outcome, female is an outcome. It's one possibility, one particular identity that could be uncovered. It's one member of the outcome space, or one member of the sample space, right? So the sample space for majors in this class was history, psychology, and sociology. So an outcome is just one of those things. Okay? How about the outcome space? Yeah, it's the collection of all of the potential outcomes that there could be. So the collection of all possible outcomes that could occur during a statistical experiment. This is like a population of outcomes, right? This class is a population. It's a small population. There's a population. The point, if we think about the outcomes, like the potential, I mean, you could flip a coin now, you could flip it later, you could flip it in this room, you could flip it somewhere else. So there are lots and lots of individual things that you could observe, but they all fall within one of two categories, which is heads or tails. It defines the population of interest for us. Does that make sense?
Yeah.
All right. So this is a bit recursive. Statistical experiment is a well-defined procedure that results in the occurrence of some outcome, which is a member of the outcome space, which is a collection of things produced by a statistical experiment. This is recursive. This is bad when you want to define things, so my apologies. So let's try to look at some other examples. So I'm a cognitive experimental psychologist. One thing that I'm interested in is how quickly people can perform tasks under different situations. One of the current things that I'm looking at is, are people able to complete their searches faster when they stand up or when they sit down? So if I'm interested in response time, which is indexing how quickly they're able to complete their searches, like what would the statistical experiment be?
Are you going to go into like the details where you're going to have a control group and the experimental group?
No, when I talk about a statistical experiment, this is very different from what you will talk about as an experiment in research methods. So in research methods with an experiment, you typically have a control group, an experimental group, you have random assignment, random selection, you have a lot of things that make up an experiment. But with a statistical experiment, it's just some well-defined procedure that results in a particular outcome. Okay?
In that case, you'll have to have a group of students that will try it sitting and try it standing and check with the differences.
Now, I don't need a whole group of students. I just need one student at one time, right? Because a statistical experiment is a well-defined procedure. It's going to look for one outcome. So if we're talking about a whole group of students, this would be a whole bunch of outcomes, right? So what would this statistical experiment be? Back before people had computers, how would they do a statistical experiment? You want to see how fast someone can run 100 meters. How do you do it?
You run.
You run, okay? You need someone to run. What else?
You needed some sort of time measurement.
You need some sort of time measurement, so we've got a stopwatch.
Yeah.
What else?
Like this.
You compare the two situations. You compare, for example, when he's sitting and when he's standing.
Okay, let's stick with the running thing right now. We can go back to sitting and standing in a minute. But so the running, if we just want to figure out how long it takes for them to run 100 meters, we need someone to run, and we need a stopwatch.
And
What
we
else?
people
We need people to do what?
to run.
You just need,
And
for a
another
simple
person-
experiment, we just could do this one time. That's a simple experiment. It's a statistical experiment, okay?
You have to find a place to run.
Okay, you need a place to run.
Observe
You need an observer. What do you need the observer to do?
to like measure the time
Okay,
and
how do you do this?
push the button.
Push the button. When?
When the person starts running.
When the person starts running, when the person stops running. That's exactly right. Right? You want a statistical experiment? Go! You press the button.
Yes.
They cross the line, press the button again. Right? That's a well-defined procedure. We're going to start the timer at one time, stop it at another time. The times that we're starting and stopping are very well defined. And what will they give us? They will give us
A number.
a number which we have called
A variable.
it is a variable, it is, but I haven't called it that yet in this class.
An outcome.
An outcome, that's exactly right. So, the statistical experiment, when I do it with the standing seating thing, I measure how many milliseconds it takes people to respond to a stimulus. So I show them something, the search display, and I start the timer. And then they press a button, whether they found it or they've not found it. They say it's there or it's not there. And then I stop the timer. That's my simple experiment, and this produces an outcome. Maybe 483 milliseconds. If you're running 100 meters, it might be like 4.83 seconds. That's pretty fast, I think. I'm not very good with the metric system. I'm American education, pardon. Okay, so we have one particular outcome. What is the outcome space? What potential outcomes could we observe? Anything?
Infinite.
Infinite. What do you mean infinite?
I'm not sure.
I can define a sample space. Infinity is part of my sample space, but let's define it better.
From 0 to infinity.
From 0 to infinity, right? Yeah, from 0 to infinity. So you got part of it, right? We could observe 483, we could observe 212, we could observe 1, maybe 0, not anything. Not negative infinity, not negative 24.
Anything
Right?
in between that.
That's right. Anything between 0 and some infinite number of milliseconds. Yeah.
How come 0 is included?
How come 0 is included?
Yeah, I mean, it takes you time to respond to a stimulus, even a very tiny part of a millisecond.
If he doesn't know,
If he doesn't run, it'll be infinite, right? He'll never get there. So why include 0? I wasn't meaning to talk about this today, but this has to do with precision of measurement. So really, like, you don't have to look at milliseconds. You could break it down to microseconds or nanoseconds or other things. And for some particular statistical experiment, you might never ever observe 0. So in the running example, you're not going to observe 0 milliseconds. You're not going to observe 0 seconds, right? But we don't know what the lowest is. What's the lowest? Is it 4.83 seconds to run that far? Or is it 5.29 seconds? Or is it, I don't know. We can run a whole bunch of statistical experiments to try to estimate what the lowest would be. Okay? Anyway, imagine that we're looking at accuracy instead of response time. So I might not want to see how fast someone responds. I might be interested in how accurately they respond, right? So when I give you guys grades, your grades are based not on the speed that you guys respond, but the accuracy of your responses. So if you finish the exam in 10 minutes and everything is right, and you finish the exam in 2 hours and everything is right, you're going to get the same score, right? So I don't care about response time all the time. Instead, I care about accuracy. So what's a statistical experiment you can do to assess accuracy?
You correct it, either it's right or wrong.
Yeah, so what do you need to do in order to correct it? Let's break it down. I mean, these are sort of dumb kind of questions because they seem so obvious, which I think is why it's taking a second to respond. But this is important because we need a well-defined procedure, right?
You have to have exams, so you have to give the person the shit pick. You have to then have a time, start the time.
We don't need the time. We're looking at accuracy. Time doesn't matter.
You need to have a sample answer, and then you compare.
That's right. So we have an answer whose accuracy is in question,
Yeah.
and we have a key. And we do this comparison. And then we say, are these two answers close enough? Right? So the statistical experiment would be to compare a student's answer to an answer key. Notice I have a student's answer for one outcome. Yeah.
can you say that there is a control group?
In what sense?
Answer key. You don't have it before.
So usually, this is more of a research methods question, but a control group is not necessarily the answer key. It would be something that has been manipulated amongst people. So I give half of the class homework. Really, I tell everyone that the homework isn't up yet, but it actually is, but I'm only giving access to half of the students. I sent them individual emails. So then what I do, I might look to see whether accuracy depends on whether or not they got the homework. Does that make sense? So the control group would be the group that didn't get the homework. The experimental group would be the group that did. The answer key is just something that I use in my statistical experiment to determine whether or not the student's answer is a correct outcome or an incorrect outcome, which brings me to the second part. Does that make sense?
Yeah.
So the outcome could be that they're the same thing. That is, they're correct. What's the outcome space?
From right to wrong, it can be two.
Be correct or incorrect, right? Wrong. Same, different, right?
But in some, like, especially like in multiple choice question, it is actually same or different. But in like essay questions, this is why some teachers give you half mark. So like maybe there is a third possibility to
Well, it depends how you define statistical experiment. Typically with an essay question, like you get points for parts of answers, right? So each little part of the answer is one little question. So if I had you guys do an essay on how do you know that the probability of a fair coin turning up heads is 0.5, you might say, well, the outcome space, there are two potential outcomes. And I say, oh good, they got that part right, 1 point. Oh, and there's this probability function, blah, blah, blah. That's another part. Does that make sense? In that case, we would define a different outcome space. But for this outcome space, where we're using like a multiple choice, what's the outcome space? 2. Correct or incorrect? Great. Religious preference. How do you measure someone's religious preference?
Again, you can have options like maybe for, like Hinduism, Buddhism, whatever, and other, and it can be one of the categories, and you just check it out.
So, I write a question. Please indicate your religion. Muslim, Christian, Hindu, Buddhist, atheist.
Jew, other.
We can make a really huge outcome space if we wanted to,
Yeah.
right? Or maybe we could do something simpler if we wanted to. Maybe we just want to see how many non-Muslims are at Shia University. So we'd say Muslim, other, right? So we could have Muslim as an outcome depending on how we phrase the question and which opportunities we have for people. We can have different types of outcome spaces, right? So, back to the question. So we know the outcome space. Outcome space is ridiculously easy. It's heads or it's tails, right? We have a statistical experiment. We're going to, in my case, the way I do this is I flip it with my right hand, I catch it with my right hand because I'm not as good, and then I pop it over. And I look and see what side is up. That's my statistical experiment. It's heads. So what's the probability of observing heads? 0.5 dub. So how do we know? I think earlier you said because there are two outcomes in the sample space,
Yes.
right? We have two outcomes. There is heads, there is tails. That's it. There are two outcomes that we could see. Heads is just one of those outcomes. Therefore, we take the outcome that we're interested in, heads, and divide it by the total number of outcomes. 1 divided by 2 is 0.5. Does that make sense? Is that what most of you guys are thinking? Who is thinking something different? Oh, that's really annoying. Were you thinking something different? No, everyone was thinking this. Everyone agrees with this. Wrong! Oh, why? Why is it wrong?
Because of the chance, I don't know, maybe it can be,
Well,
Of this. But in my statistical experiment, I've said, if it does this, I'm going to flip it again. Right? So we ignore this. So just forget about turning up on its end. Forget about it. So what's wrong with this?
is it fair?
Is it fair? Well, we've, if we go back a ways. Yes, what is the probability a fair coin will turn is actually the critical question. Is the coin fair? Why is it so important?
Can be biased.
Because
The coin could be biased, right? The coin might not be fair. The probability of getting a heads could be 0.6 if it was biased towards head, right? So now when I set up the question and I say, what's the probability that a fair coin will turn up heads, what else do you know?
So,
You know more than just what's in the outcome space. You know more information.
what's wrong?
So what's wrong?
yeah, it's a fair coin. It's a great coin. So we looked at 10,000 times, and the overall frequency, it was 0.5? Near 0.5. Maybe. Actually, if we did it 10,000 times, it would be very close to 0.5. And I'll show you that in a little bit. I'll give you guys the answer so you don't have to wonder, well, why is this wrong when it seems so right? So, let's take another example. Let's imagine that I'm going to pick a student from this class at random. What is the probability that they're a psychology major? We need to know the outcome space, right? We've already defined the outcome space. Up here I said psychology, sociology, history, CS, business, literature, CTV, politics, whatever. Anyway, we know that this is the wrong outcome space for this class. Right? For this class, what's the outcome space? Psychology, sociology, history. There are 3. So, if we did the exact same thing that we did for the coin and we said, well, there are only 3 possibilities, there are only 3 outcomes, there's psychology, history, and sociology, and psychology, the one that we're interested in, is just 1, we divide 1 by 3.
Objection.
No, objection. No, yes, what?
Yeah, because in the second example about the class, the ratio is different.
The ratio is different.
Yeah, but in the first one is 1 to 1. So it's one of the positive. But now we have so many psychology students. You cannot compare one history student to I don't know, I think 40 or 35 psychology students. So the ratio is different. So the probability has to be different.
The number of outcomes.
The number of outcomes is the same.
No.
There are only 3 outcomes.
But in the first time we have the test, outcome space and 2.
Uh-huh.
There's only 2. So the ratio is
Also,
I'm not sure I follow. So with this we have 2 outcomes. With the majors we only have 3 outcomes. I'm not looking to see whether you're CBEL or Zainab or Anas. I'm not looking at that. I just want to see if you're a psych, history, or sociology major. Only 3 outcomes.
what numbers of students?
The number of students is not equivalent. There's, all I said, the ratios are different. The key thing that allowed us to answer this question so easily is, 1, we know for a fair coin how many outcomes there are. But knowing the number of outcomes is not enough. So the way that I phrased it earlier, right, there are 2 outcomes, and heads is one of them. It's not just that there are 2 outcomes. It's that there are 2 equally probable outcomes. Right?
Are you trying to say what is mutually exclusive or conditional dependence? That?
I don't want to talk about mutual exclusivity and conditional probabilities yet. We'll start talking about that next class.
So I don't think how could be wrong.
What can be wrong?
Because it's 0.5 because
No, the answer is correct. 0.5 is the right answer, but how we got to it here was wrong. It's not just knowing the number of outcomes that will allow you to compute the probability. You need to know how probable the different outcomes are to compute the probability. And we know that there are 2 equally probable outcomes here. So if instead I said because there are 2 equally probable outcomes in the sample space, and heads is one of them,
then that would have been right. The distinction is subtle, but it's important.
So
Because otherwise, you can, compute probabilities in the wrong way. And everyone agreed, no one picked up on this tiny little error that makes this statement wrong.
Maybe.
So it would be like it has to be the same person, the same environment. Like,
No, I can flip the coin in here, I can flip it out there. I can sample my, the psychology, the students from my class here, I can call them randomly at home. It depends how I want to define this statistical experiment.
yeah.
Does that make sense? If I do them in different environments, things might change. So if I were to randomly sample this class today, this class doesn't represent the entire population of students taking my class this semester. Some people are absent, right?
Yeah.
So if I really wanted to sample adequately, I would need to be able to get those people who aren't here as well. Okay? All right, so as we said, the probability is much higher. I guess the probability here would be like 60, 70%. Can all the psych majors raise their hands? Yeah, looks about 60, 70-ish. All right, so what went wrong? The different outcomes aren't necessarily equally probable, as you guys have figured out. What we need is some type of function that assigns each outcome the appropriate probability, right? We'll call this a probability function. After we have assigned each outcome its probability, then we can answer the previous question for anything. Whether it's religious preferences of people in Istanbul, whether it's gender of students at Bilgi, whether it's whatever. All right. So the probability function for a fair coin, right? The probability function for a fair coin is really, really well known. By definition, the fair coin, both sides are equally probable. The probability function for a fair coin says that the probability of a head is 5, and the probability of a tail is also 5, right? This, P something, what this means is probability of that thing, of that outcome. So probability of heads is 0.5. Probability of tails is also 0.5. Now note, the probabilities for all of the outcomes within the sample space, or the outcome space, add up to 1. Right? So if there were, let's say, 70% psychology majors, and we had 25% sociology majors, how many, or what percent of people would be history majors in this class? 5%, right? They have to add up to 1. We only have 3. We know that 2, that last one has been determined for us, right? This is the second axiom, pardon. This is the second axiom of probability. Axiom.
What does that mean?
So, like, there are like laws of thermodynamics. Like an axiom is like sort of like a mathematically defined law. It's the way that I was not expecting this question. So it's basically like a rule describing probabilities for all types of events. So one of the rules for probability is that the probability of all of the outcomes is 1. If you look, what's the probability if I randomly sample from my psychology class that I would get someone that was in my psychology class, right? 1. All right, I will look up the definition of axiom. I encourage you to look up the definition of axiom yourself, and I'll try to get back to you in the next class with a much better, more eloquent definition. Thus, if we have this probability function, then we know that the probability of getting a heads isn't 5 because heads is one of the 2 outcomes. It's 0.5 because that's the value that the probability of function is assigned to it. Now, we can create probability functions in a number of ways. This fair coin thing, this is a theoretically determined probability function. Right? We have a theory about what it means for something to be fair. If it's fair, that means that all of the outcomes are equally likely. If I have a coin, heads is just as likely as a tails. If I have a die, a 1 is just as likely as a 6, which is just as likely as a 2, which is just as likely as a 3 and a 4, and whatever one else I missed. So, for a fair coin, each outcome has the same probability. Imagine that we have our sample space, or our outcome space. The probability that we observe something in that outcome space is 1. Thanks to that axiom we talked about earlier. Now we have the heads. Probability of the heads is 0.5. And the probability of the tails is 0.5. They have the same probabilities. For a fair die, each outcome also has the same probability. Sometimes probability functions aren't defined by theory, but they're defined by the population of interest. Let's hope my time will work. Yes. So we have psych, we have history, we have sociology. How many psych majors? Please raise your hands. Hi. Let me put my glasses so I can see you. Once I have counted you, put your hand down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Whoa, psychology in the house. How many sociology majors? 1, 2, 3, oh shoot, 4, 5, 6. The sleeping person? 7, 8, 9, 10. Did I get you? All right. 10.
No, not sorry.
Whoa. Ugh. History. Hey, Mama. All right. So now let's talk about people. Now we can talk about Sibel and Dennis. Well, the rest of you. Let's say if I were to do a statistical experiment, the chances of me getting, or the probability of me picking any one of you individuals is identical, right? So I have just as much of probability of picking her as I do her, as I do him, as I do him, as I do her. Does that make sense?
Yes.
So all of the people are equally likely. If that's the case, then I can create my own probability function. So the probability of some outcome is the proportion or the relative frequency that that outcome occurs in the population. So for our class member, we can divide the number of psych majors by the total number of students in this class. My math isn't that great. So let's go to R.
Yay.
So we have 32, 1 and 10. Actually, I'm good enough. That's 43, right? 32 plus 1. 32 plus 1 plus 10. So we have 43 total students. What's the probability of us observing a psych major if we pick a student at random from this class? Okay, Maverick, did you respond?
2 divided by
32. The number of students that we could observe that are psychology majors over the total number of students that we have.
0.7.
So, P psych equals 32 over 43, which equals, oh there it is, 0.744. Right? Going on. The probability of a history major?
1.40.
Yes. And the probability of sociology?
Lower.
Actually, I should have just realized that I could just remove the decimal place once. So, cool? So we didn't have a theory. We didn't say like, oh, you know, I think Dr. Knapp's class should have about 70% psychology students. I mean, by looking and by having you guys raise your hands, I was able to come up with a rough estimate of what those probabilities might be. But by looking at the whole population of the students in my class today and getting all of your guys' major, I can directly calculate the probabilities of a statistical experiment looking at the majors of the people that are here today, what those probabilities for the different majors would be. Make sense? So we can create probability functions with a theory. We can also create probability functions by using relative frequencies. So here's one that I created. Thought we'd have more diversity in our class, but we don't. We have outcome spaces. Our outcome spaces is much more restricted than this. Actually, we can use the same outcome space and we'd have things like business, 0 students. What's the probability? 0. Cinema and television, 0, 0. Right? We can keep those in our probability or in our outcome space, but the probabilities associated with those outcomes are 0.
And they don't all add up
Yes, that's exactly right. They all add up to 1. The probabilities are all real numbers that are greater than 0, which is, or greater than or equal to 0, which is the first axiom. And the second one is that they all add up to 1. You can't have a negative probability. What's the probability that the coin will turn up heads? -2? No. They have to be greater than 0, and they have to add up to 1 if you look at the entire outcome space. Groovy?
Yep.
So let's visualize some probability functions. So for a fair coin, this is what the probability function would look like. I have probability on the y-axis, and the 2 outcomes that could appear on the x-axis. We have heads, we have tails. Both of them have a probability of 0.5. Does anyone know what type of graph this is called?
Bar graph.
It's a bar graph. Why would anyone call it a bar graph? It looks like bars. That's exactly right. Yeah, this is used for qualitative data, as she mentioned. So it's not like heads are more of something than tails are. They're different outcomes. In America, they have this cereal called Lucky Charms. Has anyone had the luck to eat Lucky Charms? There are different marshmallows in Lucky Charms. There are green diamonds and purple horseshoes and lots of other marshmallows too. But each of those types of things would be a qualitatively different outcome. These are qualitatively different outcomes. Male, female, these are qualitatively different outcomes. My example class, we have psychology, we have sociology, and history. The number of students here, so this was not the example class here, but was this, which is nothing actually like the class that we defined. If we were to draw this instead, we have 32 psych. We have 1 history. And we have 10 sociology. Right? Now, notice here we're talking about probability, and here I have the frequency of the particular outcomes, the number of students that we observe in those different categories. Now, we can create the probability bar graph directly simply by dividing them appropriately. So, psych, we said it was 0.744. So that's about there-ish. Soc was 0.232. About there. and other 2, it's about there, right? So basically, we've got the same thing plotted in both graphs. It's just representing the information a little bit different. Okay, sometimes you don't know what the probability function is. So let's say, what's the probability function describing the political orientations of Istanbul's residents? So what different political parties do you have?
FKP,
There's AKP,
JHP,
CHP, MHP, my favorite, which is the Kebab Partisan. There are lots of parties. How many citizens, I forget citizens, how many people live in Istanbul?
20 million.
60 million?
They say 20 million. But
It's a lot, dude. Yeah, I would have guessed like 12 million, 20 million, 14, 16. It's a lot of people. How do you determine what those things look like, what the bar graphs look like for Istanbul?
well, the numbers will represent millions instead of just normal joke. When you write up to 20.
Okay, so instead of going, 1 to 50 or 1 to whatever, you go 1 to like millions. No?
No, you won't choose that type of graph. There's a different graph for that type of graph. You won't choose a graph.
Well, we could use a bar graph. You would have a lot of bars. You have a big bar for AKP, a big bar for JHP, tiny little bar for the Kebab Partisan. But we could use a bar graph to represent those data. But how do we get those data? How do we determine the probability function for that?
Instead of having to write 1 million.
You have to look at the last census, the population census.
Okay, so we could look at the population census.
But it's
The
hard.
census, I don't know the plural of census. Is it censi or censuses? Anyway, in the last census, does anyone know if they asked for political affiliation?
They don't.
No, they don't. Yeah.
They don't. I was going to say, they shouldn't. They might want to know, but they really shouldn't be asking. So, barring the census, where we actually have the data for everyone, how can you get this? I mean, can you go out there and get every person in Istanbul?
You can choose a random sample.
You could try to get a random sample, right? Pick people at random in Istanbul, right? How big?
Well, how big that depends on how much money you have.
Okay?
How much,
This is going to cost a lot of money.
yeah.
I mean, if I want to go and ask lots of Istanbulians, all 12 to 20 million of them, whatever, it's going to take a lot of time going around and asking them, right? And I'm going to miss some because when I went to her house, she wasn't there. She was sick. I went to her house, she's taking my class. Mashallah. But, right? So the people aren't always there. So you need to randomly sample. So if we can't measure the whole population and we don't know what the distribution is, we need to make inferences, right? We need to make inferences on data that we collect. So how do we do this? We do statistical experiments. Let's ignore this question for the moment because this is a really big question. Let's go back to flipping coins, which are really easy. Let's say you have a fair coin, but you didn't know that it was fair. So we have a coin. Is this fair or not? I don't know. I want to find out. I want to find out if this is a fair coin, right? So how can we infer the probability distribution? What do we need to do? I said statistical experiment.
Flip the coin.
Flip the coin, right? So we can look at the sides of the coin, see what outcomes could occur,
Yeah.
and then we start flipping the coin and see what happens. Use statistical experiments to sample the sample space, or to get outcomes from the outcome space, right? So how big should our sample be? Well, let's take a look. So sample size 1. If we flip the coin once, this is one statistical experiment, we observe something. I said it was heads, I was wrong, it was actually tails. That's one outcome, right? So if I wanted to draw an inference from this one outcome, what would I say? What's the probability of observing heads?
It's 1.
25.
If this is the only data I collected,
It's 1.
the best inference I could make was that it's 1. If that was what I observed, I would say probability 0, right? So probability of heads is 1. Oh, okay. Let's do this 1,000 times. Let's do 1,000 of these with a sample size 1 and see how far off our inferences are on average. This is where R comes in handy. Don't get too upset. This is really, it's fairly easy. It's easy. You know, my kid asked me one time, I forget what profession it was, but it was like for people that like make race cars or something. He's like, Dad, is that hard to do? I'm like, no, it's easy. They're all experts. They've all spent a lot of time doing that. So they find it very easy. Teaching for me? Easy. I don't know if I'm any good at it, but it's easy because I've had a lot of practice, right? So if you're like, ooh, all you need is a little bit of practice and you'll be all right. Okay, so here's some code. Look, sample size equal to 1. Oh my goodness, that code, that's so hard. Ooh, sample size 1. How many repetitions did I say I wanted to do?
1,000.
1,000. Oh, so hard. What's the probability of getting the heads?
1.
Now, I said that the coin was fair, right? The coin in actuality was fair. I just wasn't sure, so I want to test. So if the coin is fair, we have a theory that tells us that the probability of a heads is 0.5. Oh, so hard. Okay, this part actually gets a little bit more complicated. What I'm doing here, this R binom, is randomly sampling. Yeah, so I'm randomly sampling from a binomial outcome space. That means it can take one of 2 events, right? So let's say heads is a 1 and tails is a 0. Okay? So I give it the probability of one of the outcomes. And I'm saying the sample size is 1, and I'm saying let's do 1,000 repetitions of this. Boom, done. Now, if I want to see how far off my guesses are, what do I need to do? So how far off our inferences are on average? What I'm going to do is don't get scared. What I'm going to do for every single observation that I take is I'm going to look at the proportion of heads that I got. So here I got 1 heads. And the true probability or the true proportion that I should have gotten was 0.5, right? So I'm subtracting the truth from what I actually saw. This is a difference, right? Now, imagine if I'm doing this. Sometimes I'm going to get heads. I'm going to be off by 0.5. Sometimes I'll get tails. If I define tails as the 0, then I'm off negative 0.5. If I average these 2 things together, what's going to happen? Positive 0.5, negative 0.5. Right? They'll average out to nothing, right? They'll cancel one another. So since I don't want to do this, I'm just going to take the absolute value of this and divide by the number of observations that we get. So hopefully you'd expect that we'd be off by 0.5 on average for doing this, right? The probability of heads is 0.5. We're estimating it to be either 1 when we observe the head, or 0 when we don't observe the head, right? So on average, we're off, at least the absolute value of these differences we're averaging 0.5 off, we're off by 0.5 every single time. So let me get back to R and show this to you. So here I just define my function that does this, creating this function sample differences, taking the absolute value of samples, which is the number that I observed in that sample divided by the sample size, which gives me the proportion. Right? So the number of observations that I had where it was heads over the total number of observations that I did, and then subtracting the probability of heads from it. So if I look at sample diffs, look, every single sample, absolute sample difference is 0.5, right? As we would expect. So, if we take a sample size 1, our estimates, our inferences, how good are they?
It's, there's no problem with the inference. It's what it is.
There's no problem with inferences. It's what it is. Is that right? Is this a good inference? Is this coin fair? Nope, it comes up tails 100% of the time. I have a problem with that inference.
If it comes up like that, yeah, then might be.
You have to repeat it.
I have to repeat it, right? Not just repeat the number of things, but I need to get a larger sample size,
Yeah.
right? So, for the sample size 1, our inferences are pretty poor. We are never right on, and we are always 50% off. 50% off every single time. That's pretty pathetic. So let's do it twice. Flip the coin twice. Heads. Wow, it actually worked out just like this time. Heads and tails. So what inference could we draw?
We
We had head once, we had tails once. What's the probability of getting heads?
0.5.
0.5. Great. Let's do this 100 times and see how far off our inferences are on average. Wow, okay, so now if we flip it twice, what this is showing us is the absolute difference. This is actually a histogram. It looks like a bar graph, but it's a little bit different. Because these values between 0 and 0.5, like, you can further divide them. It's not like males and women where you get like, oh, I'm 30% woman. You know, you're like, yeah, you're a woman. Unless, forget about the XXYs and the whatever. Right? So here we have a histogram. Notice we have a lot of times when there's no difference. So the absolute difference here is actually 0 half the time. And the other half the time, roughly, it's 0.5, right? Because if I flip the coin twice, I could get heads, 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 tails, tails, heads, and heads, heads, right? Tails, tails. Yes, thank you. Tails, tails. Right? So when I get these events, I infer the probability to be 0.5. When I get the other events, here I estimate it to be 1, here I estimate it to be 0. So half the time I'm estimating the probability correct. The other half of the time, I'm still off by 0.5. So I'm going to stop running the R, because we're running a little low on R. Where are we? Here. So if we do this, boom, we get this. These graphs are going to be a little bit different because each time you do this in R, it gathers new random samples. All right, so the vertical line here shows the mean absolute difference. So we're off by 0.5 here, we're off by 0.5 here, we're not off at all here. So 0.5 plus 0.5 plus 0 plus 0 divided by 4 is 0.25, right? So the average that we should be off is 0.25. Wow, that's very close to what it actually was. All right, let's do it 3 times. We got a heads and 2 tails. If we got this, what inference could we draw? Probability of a heads is
1 out of 3.
1 out of 3, 1/3, 0.333 repeated. All right, so if we do this lots and lots and lots of times, and we see how far off our inferences are on average, we get something like this. Notice, we never have an absolute difference of 0. We're always a little bit off, but we're not off by a whole lot compared to what we were earlier. Only a small fraction of the time are we really off, right? And before, whereas this average absolute difference was basically right on 0.25, now it's shifted over. It's like 0.23, 0.24s. All right, let's do the sample size 4. Boom. Again, the absolute difference has shifted, so it was at 0.24 before, now it's under 0.2. Do sample size 10, ramp it up a little bit more. Now look, oh my goodness, the biggest error that we make, it's not 0.5 anymore.
Yeah, so the more you repeat it, the less mistakes you make.
The more we repeat it, the better our inferences are getting.
Yeah, that's
The inferences that we make that are way off, they're not as far off anymore. The worst inferences we make are still better, right? And the average inference that we make is really pretty good. And so this means that on average we're off by 0.1, so this would mean that we're estimating the probability of the coin to be like 60. I'm sorry, 0.6 or 0.4, right? So let's ramp it up even more. Let's do 100. Wow, so before we were at 0.4, now the biggest error that we make is only off by 0.15. The average error that we're making is less than 0.5. So on average, we are like within 5% of what the real probability is. So on average, our estimates are ranging between 45 and 55. So things are getting better. Let's bump it up one more time. So we do this. Wow, 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 wow. Our worst estimate was like less than 10% off. I'm sorry, not less than 10%. It was less than 0.1 off. 0.6, that's actually 12% off. But, so our worst estimates are much, 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 much better than they were before. On average, our estimates are very, very close. They're 0.01 off, basically. So after 1,000 flips, most of the times that we do this, we're getting an answer that's very close to the truth, right? Which is 0.5. So what's going on? As we take bigger and bigger samples, our estimates are getting better and better. So the law of large numbers states, basically, when you repeatedly perform statistical experiments, the proportion of times that one observes the different outcomes more and more closely approximates the probability of observing those outcomes. So if I were to draw a small random sample of the psychology majors, or of the students in this class, I would get all psychology majors in a lot of those samples, right? And I would estimate the probability of psychology major to be 1. If I were to draw larger and larger and larger samples, I should very, very rarely get samples where everyone is a psychology major. What I should get is a sample that better reflects the real probabilities in the population. Does that make sense? So how many people we want to go to look at the people in Istanbul depends on our money. It also depends how accurate we want our estimates to be. Do we care about parties that have less than 1% of the people supporting them? Do we just want to get like make sure that we are likely to get all of the parties that have 5% support or more? Right? Questions like this can help us determine how much data that we need to collect. In other words, our estimates tend to get better as we collect more data. Does anyone take calculus? As the sample size approaches infinity, this is a limit question. If you get it wrong, no big deal, because you're not supposed to have problem for calculus. As the sample size approaches infinity, what happens to the observed proportions?
They decrease.
Not they decrease. The differences between them and something else decrease. The differences between the observed proportions and the real proportions decrease. So as you take larger and larger and larger sample size, if you were to take an infinite sample size, the proportion that you should observe would be the proportion that's actually there in the population. So what is probability? We haven't defined probability yet. Someone want to take a crack at it?
We said it's, we have an outcome and doubt, and we have at least two possibilities. We have to have at least two possibilities. And in this case, it helps us to...
You don't have to have two possibilities.
At least
If you had one possibility, the probability would be one.
and we have the outcomes and doubt, we have to at least have two possibilities. And because it's one, then why are you doing it?
Maybe you don't know that it's one.
No, it has to be at least two possibilities because we're doubting it.
Maybe. What else? There's something more crucial. It's the measure of a potential for event. Probability indicates how likely some outcome is going to be. If what? If you were to repeatedly do the statistical experiment over and over again. So the proportion of times you'd expect to observe some event if you repeatedly perform a statistical experiment. The probability that this will come up heads, if this is fair, is 0.5. I would expect to observe half heads if I did this over and over and over and over and over and over again. That proportion is going to be very, very close to 0.5. So the probability is the proportion of times, or the relative frequency that you would expect to observe something if you did the same statistical experiment repeatedly. This definition works for probability functions that are theoretically defined. This works for the ones that are directly assessed. We directly assessed this group, right? But I could repeatedly sample and come up with those same numbers. Or experimentally inferred from some sample on the population like we talked about most recently. So, the study guide, you should make sure you understand what these concepts are. Come talk to me during office hours if you have questions. Shoot me an email. Next class, we will talk about more complex events and calculating probabilities for more complex events. Like, what's the probability of a heads or a tails?